So here we are in section 8. We're talking about radius of convergence and interval of convergence. So the radius is one calculation. The interval, you have to include the endpoints as well. So our first homework problem is number, I've forgotten which one it is. Hold on just a second. I forgot to copy this down when I was doing this. Okay. Okay, so we're going to start with problem number 5. So we'll do one where we just have to do the radius of convergence, and then we'll. So it's an alternating series. So the difference between these series and the series that we've been dealing with up to this point is we have this variable x. All the ones that we dealt with from section 1 through section 6 had n, but they didn't have, if we had this particular problem, we would have some number for x, 0.5 to the n. So now what we have is we have to figure out which values of x does this thing converge for. And we use the ratio test for all of these. So the ratio test, we're going to let's call, we don't call it A because it involves, it's not A sub n because it has this extra term. So U sub n is the original expression, and then we do U sub n plus 1. So we just substitute n plus 1 for n. So this becomes n plus 1. This is n plus 1 plus 1. So we get n plus 2. So what we do is we look at the limit. Actually, do we look at the limit, or do we just? Yes, we do. Okay, so you take the limit as n goes to infinity of the ratio of U sub n plus 1 divided by U sub n. And the absolute value thing, really, when you have an alternating series like this, you can just kind of, we don't have to worry about it. I mean, if we simplified this, so let's do this. I'll come back and show why you could just ignore it. So, we take this, take the reciprocal of it, so you'll end up with negative 1 to the n plus 1 divided by negative 1 to the n. And then we have x to the n plus 1 divided by x to the n. And then we have n plus 1 divided by n plus 2. So I've separated these out. So when you take the reciprocal of this goes to the denominator, this goes to the numerator, and then this goes to the numerator, or to the denominator. So you look at each one of those separately and you simplify them. So here we get negative 1 to the first power, and x to the n plus 1 over x to the n is just x to the first power. And then we have n plus 1 over n plus 2. We can't do anything with that. And what we want to do is we want to find the values for x where that is less than 1. So I was just checking. If you look at page 661, they have an example with an alternating series. Just example 4, and you can see when they go from the original U sub n plus 1 over U sub n, and they go to the next step, basically what they've done is all the negative 1 stuff is irrelevant, and then they simplify the other parts. they don't show exactly how to do that. So then the question is this true for all values of x? So what we'll do is we'll get rid of the negative term just to make it so it's easier to look at. So we have x times n plus 1 over n plus 2. Well, I can imagine values of x where this is going to cause this to be greater than 1. So but as you let n go to infinity, this term is going to become 1. Because we'll get infinity plus 1 over infinity plus 2, so you get infinity over infinity. And the question is, when can I, because that's an indeterminate result, so you're just like, hey, why did you do that? Because sometimes I get infinity over infinity, and I can't just say it's 1. And one of the reasons is because it's just infinity plus 1. It's not something like e to the infinite power or x to the infinite powers. The other thing is you could use L'Hopital's rule, and so if you take the derivative of each one of these, you'll get 1 over 1, and so it does go to 1. So ultimately, as n goes to infinity, we just get that x has to be less than 1. So that means so let's look at theorem 920. It says there exists a real number r greater than 0 such that the series converges absolutely for x minus c as the value of x minus c is less than r and diverges. So that r in this case is 1. And so our radius of convergence, which is what they're asking for here, they're asking for the radius of convergence. So the radius of convergence is equal to r, which is 1. So I'll just double check and make sure I did that correct. So look at the manual out. 9.8, number 1. So yes, you get the absolute value of 1 is less than 1. So we actually still need to keep the absolute value sign in here. So the radius of convergence is equal to 1. Okay, let's go to the next one, which is now going to do the interval of convergence. So we are going to problem number 12. Yep. So our infinite series, summation from n equals 0 to infinity of x over 5 to the n power. So u sub n is x divided by 5 to the n power. And u sub n plus 1 is x over 5 to the n plus 1 power. So we take the limit as n goes to infinity of the ratio, absolute value of the ratio of these two. So we have u sub n plus 1 over u sub n. And you see what happens is we're just left with x over 5. So we have the limit as n goes to infinity of the absolute value of x divided by 5. And you see this n's not involved in here, so all we have to do is have x over 5 less than 1. So x, the absolute value of x, has to be less than 5 because you multiply both sides by 5. So in this case, on number 12, the absolute value of 5 has to be, absolute value of x is less than 5, and so our radius of convergence is between -5 and +5. Okay, so now the question is, you have to check the endpoints. So what you do is you go back to the original series and you put in 5 for x and -5 for x. So we got -5 over 5 to the n power. and that is, so we have -1 to the n. So that is a geometric series. So the endpoints, you have to use the other tests if they're appropriate. So we go back to whatever page that is with the one I hand out in class, and you look and you say, oh, geometric series, a r to the n. So in this case, r is equal to -1, and it says if the absolute value of r is greater than or equal to 1, it diverges. So at -1, it diverges. So that also means that the negative part of this remains just an inequality, because we can't put an equality because it doesn't work at -5. And if you do the same thing at +5, you're going to end up with this series, just +1 to the n power. And again, the absolute value of r, which is absolute value of 1, is equal to. So this other side, the right-hand side, also diverges. So this is the left-hand side, meaning the smallest side. This is the right-hand side. And so we just leave it as such. We don't include -5 and 5. It has everything in between works, but not the endpoints and anything outside. So moving on to problem 15, we're asked to find the interval of convergence. So our series 15 is summation from n equals 0 to infinity of x to the n over n factorial. So again, u sub n is just the expression in there. U sub n plus 1 is x to the n plus 1 divided by n plus 1 factorial. So to find the interval of convergence, well, to find the radius of convergence, we use the ratio test. So let's take the limit as n goes to infinity of the absolute value of u sub n plus 1 divided by u sub n. And then we take the reciprocal of the denominator here, and then we arrange them. So I'm going to put the factorials together. So you get n factorial divided by n plus 1 factorial. And then we get a numerator here, x to the n plus 1 divided by x to the n. So we simplify, and so the first ratio becomes 1 over n plus 1. Second ratio becomes x. So x to the n plus 1 divided by x to the n is x to the first power. And notice that when n goes to infinity, it doesn't matter what x value is. It'll still this will go to 0. So this equals 0 for all values of x that are finite. So in this case, we go back to our little description, page 660, convergence of power series. It says if the radius of convergence is infinity, which it is, so in this case, since this is true for all values of x, radius is equal to infinity, then this series converges for every value. So then we don't have to do the endpoints because we never include infinity. So the only time we have to worry about endpoints is when we get some number. So this converges for all values of x. And if I put x in 0.5, that's going to converge. And if I put in 5, it's going to converge for x. And part of the reason is because n factorial is always grows much more quickly than x to the n, so this thing gets small very, very quickly, no matter what the value for x is. I mean, the larger the x value, the longer it takes to converge, but it doesn't move as quickly to 0, but it always works. So that was 15. So let's double check here. So it says the limit is n goes to infinity of x over n plus 1, absolute value equals 0. The series converges for all x. Therefore, the interval of convergence is, so I have to actually write this out, the interval of convergence is negative infinity x positive infinity, but it doesn't include negative and positive infinity. Okay, so that's 15. Let's do another one, 18. So 18 is summation from n equals 0 to infinity of negative 1 to the n times x to the n divided by n plus 1, n plus 2. So u sub n is just what we have. And u sub n plus 1 so these become n plus 1, and n plus 1 becomes n plus 2, and n plus 2 becomes n plus 3. So then we take the limit as n goes to infinity of the ratio, absolute value, the ratio of negative 1 to the n, x to the n, divided by n plus 1, n plus 2, divided by negative 1 to the n plus 1, x to the n plus 1, divided by n plus 2, n plus 3. And we can, again, we don't have to worry about the negative signs. That'll be taken care of by the absolute value. So what we end up with is the x part. So you'll have x to the n divided by x to the n plus 1 from these two. And then the constant terms, these are going to go up to the top. We'll take the reciprocal of this. So the reciprocal of this is being numerator. You multiply it out. So you get n plus 2, n plus 3 here, and you get n plus 1, n plus 2 there. That's it. Okay. So in this, again, if I multiplied this thing out, the second part, you'll have n squared plus 5n plus 6. In the denominator, you have n squared plus 3n plus 2. And like before, you could use the limit of two polynomials, take the leading coefficients, which is 1 and 1 of the highest order term. You could apply L'Hopital's rules twice. Anyway, this goes to 1. When n goes to infinity. So what we're left with, and here this becomes 1 over x. So x to the n here, and x to the n plus 1, so we get 1 over x to the first power. So what do we do? So the absolute value of 1 is just 1, so I can take those away. So that would indicate for number 18 that the interval convergence is outside of the numbers 1 So let's just check, see if that's right. It's 18. So what did I do wrong there? I must have made a mistake. Oh, I switched these the wrong way around. So this should be up there. So all this gets switched around. I thought something was weird. Sorry about that. I don't remember seeing that before. That's why I was. So actually, this is going to be n plus 1. This is going to be n plus 1. Just fix all these things up. These will be to the n power. So it's u to the n plus 1 over u to the n. So I'll begin as a word of warning there. I do these mistakes just so that you can see what happens. That's a lie. Okay. So it's u to the n plus 1 over u to the n. Okay, now what happens is the negative ones we don't worry about. We get x to the n plus 1 over x to the n. In the numerator we'll have n plus 1, n plus 2. In the denominator we have n plus 2 and n plus 3. And again, this goes to 1 when n goes to infinity. So ultimately we end up with that. That's the value of x instead of 1 over x. It has to be less than 1. And the limit as n goes to infinity, actually got rid of that because when we did that, this became 1. So the interval of convergence is from -1 to +1. Now the question is, we have to look at the endpoints. So the endpoints, so we have to do when x equals -1, and we have to do when x equals +1. So if we do that, for -1, our series becomes, was it from 0? Yeah, okay. So we end up with -1 to the n times -1 to the n. So that's the second one comes by plugging in -1 for x. And we take that over n plus 1 and n plus 2. Okay, so what happens now is that when we multiply -1 to the n times -1 to the n, we get -1 to the 2n. And so we get -1 to the 2n. You add these two together over n plus 1 and n plus 2. But that becomes +1. So at x equals -1, the series becomes 1 over n plus 1 times n plus 2, which is n squared plus 3n plus 2. Okay, so how do we find convergence to this? Well, we would use the direct comparison test. So we would let a sub n be this, and b sub n would be 1 over n squared. And since this is always less than that, and this one converges because it's a p-series, converges, p-series, p is greater than 1, p is equal to 2, which is greater than 1, therefore it converges. So look on your sheet, you'll see that's true. So this one converges, and because this one is always larger than that one, then this converges. And since that converges, we do include that in it. So we can go down here and put a little equal sign. They do the same thing for x equals +1. So you get -1 to the n times 1 to the n divided by n plus 1 and n plus 2. So 1 to the n is just 1. So now it's an alternating series. You could also use direct series, but they want you to use the, I'm not sure I'm doing this right. This is 18, right? Let's see. Yeah, okay, that's right. I'm doing all right. So this one's an alternating series. So a sub n in this case is all the stuff that's not the -1 raised to the power thing. So the two things you have to do for alternating series is show that the limit of a sub n equals 0 as n goes to infinity. Well, you can see when n goes to infinity, you get 1 over infinity. So this is true. So the limit of this, you get 1 over infinity plus 1 times infinity plus 2. You get infinity times infinity, which is infinity. 1 over infinity is 0. Okay, so that's the first thing. The second thing is that a sub n plus 1 is always less than a sub n. That's the second requirement. So what you would do is you would substitute n plus 1 for n. So I get n plus 2 and n plus 3. That always has to be less than n plus 1 times n plus 2. This is a sub n. This is a sub n plus 1. So let's multiply this thing out. So we get n squared plus 5n plus 6 is less than 1 over n squared plus 3n plus 2. Cross multiply. N squared plus 3n plus 1 is less than n squared plus 5n plus 6. This on both sides. This cancel out. If we, let's say we subtract that from both sides and add, subtract. Yeah, so what we'll get, if you subtract 6 from 2, you'll get -4. -4 is less than 2n. And since n is always positive, this is going to be positive and this is going to be negative, so just based on the sign, we know that this is going to be greater than that. We don't look at absolute value. So therefore, this series converges. So the series, so therefore the series -1 to the n over n plus 1, n plus 2 converges. So that means at the other, when x equals 1, which is the other side, that converges, so we also do that. So the interval of convergence is from positive to -1. So this is problem 21, section 8, chapter 9. Actually, that looks very familiar. I think I've already assigned that one. So let's do 22 instead. So we have summation from n equals 0 to infinity of x minus 2 to the n plus 1 divided by n plus 1 times 4 to the n plus 1. Okay. So we always say u sub n is the original expression inside the summation. And then we do u sub n plus 1. So n plus 1 is going to become n plus 2. Now, one question may be, why did they use n plus 1? Well, because when n equals 0, if we had to the n power, and we had n here, when n was 0, we'd have an undefined value. So you could have started from n equals 1 and then rewritten to the n power and change everything to n. But anyway, that's why they chose n plus 1. Okay, so what we do is we take the limit as n goes to infinity of the ratio of u sub n plus 1 divided by u sub n. So we'll get u sub n plus 1, which is, got to make sure u sub n plus 1 has n plus 2 in it. And then we have u sub n. Let me fix that up there. It's a little confusing. Okay, so then u sub n has all the n plus 1 terms. Like that. So now we can take the reciprocal and kind of match everything up. So let's do the x minus 2 term. So this is in the numerator. So then the denominator is going to be the n term. Okay, so we got that. Divided by that, and then this is in the denominator to start with of the top fraction. So the numerator is going to be this corresponding term. And then we have 4 to the n plus 2 here, and then this is going to go up. So we get 4 to the n plus 1. So now we're going to do some simplification. So this is going to be x minus 2 to the, so you got n plus 2 minus the quantity n minus n plus 1. So all that's left is to the first power. Here, we just have this ratio. We don't do anything with that yet, but when we take the limit, we'll know what to do. And here we get 1 over 4, because we have n plus 1 in the numerator, n plus 2 in the denominator, so we have just 4 to the first power in the denominator. Okay, so then we let n go to infinity. This part's going to go to 1, because I have the same highest order term here, and the leading coefficient is 1. So we'll end up with x minus 2 times 1/4, and that has to be less than 1 for this thing to converge. So we multiply both sides by 4. So my radius of convergence equals 4. It's that number. Now my interval of convergence, we have this absolute value thing here. So basically that says that we take this number and we do the negative and the positive. And then in the middle we have what's ever inside the absolute value, which is x minus 4. So the absolute value can be rewritten as this inequality that involves 3 parts, and then we can add 4 to each term, and so we get that. So this is my interval of convergence, except I still have to check the endpoints. So I need to find out for x equals 0 and for x equals 8. So I go back to my original series here. Actually, let's undo that. Let's copy that, not clone it. Okay, let's try it again. Yeah, it's not showing up here. Copy. Okay, well maybe I will clone it and just drag it. So move it to there, and then we'll move it to there, and then we'll move it to there, and one more time. Okay, and let's just clone it again. We'll add another page, and we'll move it over there for the next part. So we also have to do x equals 8. Right there. Okay, so let's come back and do x equals 0. So we take our series and we substitute x equals 0 in there. Okay. bothering me here. So let me just pause it for a second. Okay, I knew something was wrong. This is, when I went from here to the next one, I stuck in 4. I'll have to explain why I knew I messed up so that you can. So that's still true. This has to be -2. So this is going to be from -4 and then at least x minus 2. Okay, now, so we add 2, so we're going to get -2 and then 6. So my center is going to be around x equals 2, and I have plus or minus 4. Okay, there we go. That's going to make sense now. So this has to be -2. So then this becomes -2. And the reason what was bothering me was that this should end up being the same as that, ultimately. Okay, so this is going to be -4 to the n plus 1 power. And then you're going to be over n plus 1, 4 to the n plus 1. So we can create this into, we can rewrite that top term. So that's going to be -1 to the n plus 1, 4 to the n plus 1, divided by n plus 1, 4 to the n plus 1. So those cancel out. So it simplifies down to an alternating series. So we get -1 to the n plus 1 divided by n plus 1. So a sub n is 1 over n plus 1. And it's alternating because of this term. So we have 2 requirements for an alternating series. One is that the limit of a sub n as n goes to infinity is equal to 0. So the question is the limit of 1 over n plus 1 as n goes to infinity equal to 0? Question mark, yes. So that satisfies the first requirement. And I need to change that to 6, I think. Is that what I had? Yeah, 6. I said I was, go back. I think I might have told you why I knew I'd made a mistake, and that was because when I put in the lower limit, this number inside here didn't match up with that thing. Okay, so we got to finish this first part. The second part is that a sub n plus 1 is always less than a sub n. So a sub n plus 1 is less than a sub n, which is, they're all positive. So we have 1 over n plus 2 is less than 1 over n plus 1. So a sub n is 1 over n plus 1. A sub n plus 1 is 1 over n plus 2. So we cross multiply. These cancel out. 1 is less than 2. Yes, that was always true. So at x equals -2, the series converges. The alternating series converges. So that means that -2 works out. And then we go to the other side. Actually, we go from n equals 0 to infinity. And when you let x equals 2, you get 4. When you let x equals 6, you get 6 minus 2, which is 4. And you see these cancel out, so we're just we end up with this series 1 over n plus 1. Okay, now in the past, a lot of times this has been the p-series. And so we've just been able to use the p-series, but we can't directly use the p-series. So we have to use the direct comparison test or the limit comparison test. Either one of those would be fine. So the direct comparison test you have to pick a b sub n such that b sub n is always greater than a sub n. In this case, a sub n is 1 over n plus 1. So we'd let b sub n equal just 1 over n. So because you have this added 1 in the denominator, a sub n is always going to be less than b sub n. So this choice of b sub n satisfies the requirement. Now this is a p-series, so I could say, but b sub n is, or if you put a summation there, is a p-series, and p equals 1, that's the exponent. Therefore, the series summation of b sub n diverges, because that's, if p is less than or equal to 1, it diverges. So therefore this diverges by the direct comparison test that a sub n also diverges. Well, actually, it's the other way. Yeah. That's not true, because that would work if it converged, but because you have to use the other thing, and that's, in this case, it's not that way, so we can't use the direct comparison test, but we could use the limit comparison test. Okay. If it was n minus 1, we could use the direct comparison test, but since it's n plus 1, we can't. So, so let's erase that. That's wrong. But you can hopefully appreciate why that doesn't work. So then you do the limit comparison test. So again, you'd still let b sub n equal 1 over n. And if you take the limit as n goes to infinity of the ratio of, I think it's b sub n over a sub n, doesn't really matter. Just so if you go to the limit comparison test, it's a sub n over b sub n. So if we put in our a sub n, which is from this original thing, so that's 1 over n plus 1, and b sub n would be 1 over n. And so if you take the denominator and take the reciprocal of that, you end up with n over n plus 1, and that equals 1. So you get infinity over infinity plus 1, so it's, okay, so that's 1, and it says if this is greater than 0, which it is, so we would say L, in this case, equals 1, which is greater than 0. So by the limit comparison test, since b sub n diverges, that diverges because since b sub n diverges by the p-series test, then a sub n also diverges. So since a sub n diverges, this is a sub n, this whole thing diverges. So this is kind of opposite what we've seen before. The interval of convergence goes from -2, and we can put the equal sign there, and the upper side is 6, and we don't put an equals sign there. Okay, let's just check to make sure that's correct. This is problem number 21. Okay, well, actually it's problem number 22. Says the radius of convergence is 4, the center is x equals 2, the interval is from -2 to +6. When x equals -2, so I'm just reading out of the answer book. When x equals -2, the alternating series, right here, converges. Okay, that's what we said. We said satisfy the 2 requirements for alternating series, so it converges there. When x equals 6, the series 1 over n plus 1 here diverges, and therefore the interval of convergence is this. They don't say why this one diverges, but it diverges because of the limit comparison test. Okay, so that's 21. I mean 22. I need to fix that, make sure I don't assign you the wrong problem. 24. 24 is the next problem. So it looks kind of similar to what we've been doing, except it starts off as an alternating series. The one we just did was not an alternating series to start with. I'm just going to pause for just a second. Okay, so we're going to do 24. U sub n. Same thing we start with. U sub n plus 1. So n plus 1 becomes n plus 2. N becomes n plus 1. Like that. Then we take the limit as n goes to infinity of the ratio of u sub n plus 1 over u sub n. So u sub n plus 1, just copy that down from over here. And divide by u sub n. Like that. Actually, I got carried away there. This is u sub n. Sorry. Okay, that looks good. And then we take the reciprocal and match things up. So we're going to have -1 to the n plus 2 divided by -1 to the n plus 1. Then we have x minus 2 to the n plus 1 divided by x minus 2 to the n. And then we'll have n plus 1 here in the denominator, which leaves n in the numerator. And the final one is 2 to the n plus 1 in the denominator to the n in the numerator. The negative thing we just don't worry about because we have the absolute value. So this is going to be x minus 1 to the first power. And we multiply by n over n plus 1. And then we have 1 over 2. Okay, when n goes to infinity, this goes to 1. So we end up with x minus 2 times 1/2. And that has to be less than 1 to converge. So we multiply both sides by 2, and then we rewrite this as the inequality without the absolute value signs. So, and then finally we add 2 to every term, and we know that. So our radius of convergence, r is equal to 2, and our interval of convergence is this. And then we have to look at the endpoints. So I'm going to copy this thing here. And see if I copy it here. Maybe that copy. Okay. And then I go paste it here. Okay, now I can go back to 2 pages. Okay, so that's it. And then we do when x equals 0, and we'll do when x equals 4 to do the endpoints of our interval. And we should be getting kind of used to this by now. So I'll get -1 to the n plus 1 times 0 minus 2 to the n divided by n 2 to the n. Okay, so this -2 we can break up into a negative part, a -1 part, -1 to the n, and 2 to the n. And then you divide by that. So these are going to cancel out. Here we're going to have so you're going to have -1 to the 2n plus 1. When you add those exponents together with the same base, you get 2n plus 1. So this one is always going to be, this is going to be odd. And what we have left is 1 over n. So because 2n plus 1 is always odd, it's always going to be -1. So we're going to end up with -1 over n. Okay, we've seen this before. This is a p-series, so this diverges. P-series. Okay. Now the second case is when n equals x equals 4. So we get -1 to the n plus 1 times 4 minus 2 to the n over n 2 to the n. So this is going to be 2 to the n, 2 to the n. These are going to cancel out. And what we're left with is an alternating series. Get -1 to the n plus 1 divided by n. So again, we've seen this multiple times. You know, a sub n is 1 over n. So the limit of a sub n as n goes to infinity equals 0. So that's the first requirement. And a sub n plus 1 is always less than a sub n. And it's positive. That's true too. We don't need to do it again. And so this one works. So this second case, it converges when x equals 4. So now our interval of convergence is going to be from, what was our values here? It's from 0 to 4. Didn't work at 0, but it did work at 4. So let's check it out here. That's correct. Okay, so there we go. That's the series. U sub n is going to be n over n plus 1, -2x to the n minus 1. U sub n plus 1 is going to be n plus 1 divided by n plus 2, negative 2x to the n. So each one of these terms I add 1 to that involve n. So we take the limit as n goes to infinity. U sub n plus 1 over u sub n should have been superscript. Okay, so let's plug those things in there. U sub n plus 1 over n plus 2 times negative 2x to the n plus just to the n. Okay, so that's that part. And we divide by n divided by n plus 1 times negative 2x to the n minus 1. So let us set that up as we normally do. Ratios here, so we're going to have here we're going to have n plus 1 over n plus 2, and then we'll take the reciprocal of that, so we'll have n plus 1 over n. And here we have negative 2x to the n divided by negative 2x to the n minus 1. And ultimately this limit, this thing here is just going to end up being 1 because we have the same highest order terms. So I multiplied these out using FOIL and multiplied that out just using the distributive property. And then here I'm going to have negative 2x to the first power because you'll subtract this. So n minus the quantity n minus 1 is the first power. Now as a limit, to take the limit to go to infinity, this is going to equal 1. So all we're left with is, and the negative sign drops out because it's an absolute value. So we just end up with the 2x has to be less than 1. And so if we divide by 2, we get x. That's the value of x has to be less than 1/2. So r equals 1/2. That's the radius of convergence. And then we take this inequality involving absolute value, and we do the negative and the positive values there. Okay, so that's our interval convergence, except we do have to check the endpoints. So let's take the original series here. Oops, I didn't mean to do that. Paste, let's save. Okay, so there it is. So we're going to have to try x equals negative 1/2. And we'll do x equals positive 1/2. Okay, so here we have this summation. So we have n over n plus 1 times negative 2 times negative 1/2 to the n minus 1 power. So what do we have? That'll be that. So we have n over n plus 1. So that's negative 2 times negative 1/2 is positive 1. And so 1 raised to any power is 1. So we can drop that term, and we get that series. Well, just the nth term, if we take the limit, so before we do the a sub n is the expression here. So if we take the limit of a sub n as n goes to infinity, that's going to equal 1, because you'll get 1 this term will become insignificant. So you get 1, which does not equal 0, so it diverges due to nth term test. So that we know negative 1/2 doesn't work. Then we go up here and we plug in positive 1/2, and so we'll get negative 1. So we get negative 1 to the n minus 1 times n over n plus 1. So this is an alternating series, but it doesn't converge because this also doesn't satisfy the nth term test. Well, actually, it's not just the nth term test because there's two things. Well, actually it is, yeah. So this still doesn't go to 0. So, the two requirements for the alternating series, this goes to 0, which it doesn't. So again, the limit is n goes to infinity of a sub n equals 1, which doesn't equal 0. And so it doesn't pass the first part of the alternating series test. So this also diverges. And so this doesn't work on either side, so we just stay with this thing. That's the final answer because both the endpoints do not converge. That's our first example where they don't both converge. Okay, then we have the last problem. Actually, let's do that separately.